Now, I apologize if we're not going to go over this in great detail, but we are going to just quickly run through a few ideas, and for those of you that want some extra time with this answer sheet or to ask me about them, then please feel free to come in and do that. We will have opportunities as we go through the rest of chapter 2 and then some more in chapter 4 to practice these equation solving techniques. Not days and days of practice, but they're going to come up in problems, so we'll continue to do it. It's one of the reasons that another good reason of taking calculus is we get a lot of opportunities to practice our trig, to practice our algebra, practice exponentials and logs, and so we not only hopefully get good at calculus, but we get much better at the algebra types of stuff, okay, and all those kind of things. And so I just think that that's another thing we do in this class that is good for us if we have to go on and take other math classes. All right, just some basic algebra things. You'll see as we get into the problems today where we get into some of this solving kinds of stuff, just some pretty simple stuff in the beginning. Then we get into this where here you've got this squared, you have to FOIL it out first and gather your x terms together. You got to gather them all on one side, set 0 over here. You know, I'm not going to be picking this up, okay? So, I mean, don't worry about making it perfect and everything. But it was just an opportunity to say, hey, these are the types of things we need to be able to solve and work with, okay? So right here, we gather the x terms together. Turns out it factors, we get this. Here's another type of factoring scenario. You have x minus 2 cubed and x minus 2 squared. You can factor out an x minus 2, actually 2 of them. You can factor out 2, and we run into these kind of problems as well in our algebra situation, in calculus type problems where we need to do this. So we factor out 2x minus 2's. It's kind of like factoring out 2 x's, right? You factor out 2x minus 2's, that leaves you 1x minus 2. You factor out 2x minus 2's from here, it leaves you just a 1. Because again, if we distribute x minus 2 squared times x minus 2, it'd be x minus 2 cubed. X minus 2 squared times 1 would be x minus 2 squared. Well, now x minus 2 minus 1 is just x minus 3, and then we get our solution. So that's a factoring thing. Probably haven't done a lot of those like that, but that's what we have there. Okay, number 7 is just a basic factoring one, but number 8 doesn't factor. So we got to remind ourselves about the old quadratic formula. That's not something that comes up a whole lot, having to use a quadratic formula, but you certainly need to know that that's one way to solve a quadratic equation. You end up with a negative under the square root, that means no solution. Now, what's important for us to know is understand from a graphical perspective. This comes up a lot in problems. I would hope you would look at that and think of a parabola. Right? Isn't that what we're doing? We're saying, where does that parabola equal 0? What's it mean for a parabola to equal 0? Where's it cross the x-axis? Well, if there's no solution, that means what? It doesn't cross the x-axis, so we must have that. That's why there's no solution. This actually related to one of the problems, number 46, I think, in the 2.4 homework. It has this kind of a situation. What are the different possibilities? You could have a parabola come down and just touch and cross once, or it could cross twice, right? You could have no solution, you could have one solution, or you could have 2 solutions with a parabola, okay? All right, so there's that. Then we get down here into, this would be some cross-multiplying business here. What I did was cross-multiply. What some people did was move this over and get a common denominator. And I could see why you might want to do that since we've been doing that work on common denominators. That should work too. But anyway, it turns out when I cross-multiply and you get all this, well, you gather all your terms on one side. It turns out it doesn't factor, so you go to the quadratic formula. Now, most of these I intended to be in no calculator situation. So your final answer would be this right here. Okay, I put the decimal equivalent there just. On this one, what I did was I could have got a common denominator, which would have been 2x, and then multiplied by a 2x on both sides. Or another technique is to just multiply both sides by 2x right away. And that clears out the fraction because the 2's cancel here and I get x squared. When I take 2x times this, the x's cancel. 2 times 2 is 4. So that's how that works. And then on the other side I get 4x. So by just multiplying by the common denominator both sides of the equation, I clear out the fraction. It's kind of like if you had a 1/2 and a 1/3, you multiplied everything by 6, you would clear out the fraction. Okay, and then I just gathered my terms, and then it didn't factor either, so we had a quadratic form. Okay, and then this was just a little, this was just kind of in reverse. If these are your solutions, that means your quadratic equation must have looked like that. 3 would be a solution there, -1/2 would be a solution there. And then I FOILed it out. I didn't like the fractions there, so I multiplied everything by 2. But either way, that's not as big a deal there. Okay, the backside is where more people had questions, but yeah, I'm going to comment on a couple of things. This problem came right out of Appendix E that we did the first week of class. Divide by 20, e to the 0.1x equals 4, do the natural log of both sides. Or we had that thing where when you do a natural log, I didn't write it there, but if I did, this would be ln of this side. You bring the 0.1 down in front. ln e is 1. Everybody's got to know that. ln e is 1. Everybody's got to know that. ln 1 is 0. You've got to know those two facts. Okay? So you do natural log of both sides, and you solve it like so. That's just kind of a 2 to the 3rd. That's just a log form 1. Here you get the log by itself. Let's talk about 15 here. This is kind of an interesting one. First of all, when you have an x up in the exponent, you should do the log of both sides. This happened to have an x on both sides, which is fine. Do the log of both sides. Now, why is that a good thing to do? What can you do then? Bring the exponents down in front, see? And then now the x's aren't up in the exponent anymore. So you bring the x minus 1 down in front. Of course, it's got to have parentheses around it. You bring the 2x down in front, you got 2x ln e, but what's ln e? Ln e is 1. So that becomes this. Now, this is the part that I had discussion with several people this morning that they kind of wondered where that came from. Well, think about it. And again, you've probably never seen a problem quite like that. Yeah, I understand. Let's think about it. If I gave you that, I bet you know what to do next. You distribute, right? You distribute the 3 through there. Because what do you want to do? You want to gather your x terms together, right? What's ln 5? Just a number. It's just a number, like pi or e, ln 5, just a number. So what we have is a number out in front of this, so I distribute it. So I distribute ln 5, I get x ln 5. ln 5 times 1 is ln 5. On this side I have 2x. Now what do I want to do? I want to gather my x terms together. I want to get the x terms on one side. Well, here's an x term and there's an x term, so I'm going to subtract my 2x over to here. I'm going to add the ln 5 over to here because it doesn't have an x on it. And now what do I want to do with my x terms now that I got them gathered together? Well, yeah, I want to combine them, right? If I got a 2x and a 3x, what do you got? Now, most of you don't think of it this way, but why is 2x plus 3x 5x? Isn't it because you factor out an x? I mean, what it is you learned in algebra that they're like terms and you can add like terms. That's what you learned. But what it really is you factor out an x. And 2 plus 3 is 5, and that's 5x. That's why 2x plus 3x is 5x. Okay? Problem is you learn that in algebra before you learn about factoring, right? So your teacher just says, hey, they're like terms, add them together. Okay? 2 apples plus 3 apples, right? I mean, that's how you learn it. But what you're really doing is you're factoring out an x. So we factor out an x. And so we get ln 5 minus 2. That's just a number. ln 5 minus 2 is just some decimal. Okay? And then we divide by that, and there it is. Okay? So again, I like a problem like that because it really makes you think about the process of solving equations. We just rotely memorized this process of gathering x's and stuff without really maybe understanding what the actual what that looks like. As soon as it looks a little different, we kind of fumble. Anyway, so that's kind of different. 16 was kind of different. But we see stuff like this as we go through the year. It's important to know that e to the 2x is the same as e to the x squared. Because when you have a power on a power, what are you supposed to do? Multiply the powers. So e to the x squared is e to the 2x. So if you think about this, this is just a trinomial that factors like this. E to the x times e to the x is that. Outers and inners. So you set each one of those equal to 0. So e to the x equals 2. That'd be ln of both sides. That'd be ln2. E to the x equals 1. Well, that's just 0. ln1, which of course is 0. And I put the decimal there, but you could have just left it ln2. Okay? Section 2.5 is about exponentials and logs. Section 2.6 is about trig. So we are going to get some practice on these as we go. This is just kind of a basic trig one. Hopefully by the end of chapter 2 here, when we take our quiz, we got a couple quizzes left before Christmas. Probably another daily assignment. I put a daily assignment in this morning. I don't know if anybody noticed. It was looked at it yet, but this morning I put like a 16 point. For a lot of people, that was pretty good. If you've had your homework done, mostly when I've come around, you got most of those points. So sine x equals a half. So hopefully we get to the end of chapter 2. This would be very easy right here. This would be a very easy trig. Divide by 2, where does sine equal a half? Well, that's a pi 6. You can draw your triangles. You know, we've reviewed that already once, but if you need some more trig review, want to come in as we get into that section, that's going to be a lot this week. We'll be getting into it a little tomorrow, practicing more on Wednesday, probably even more Thursday. We may have a quiz Friday, or it may be next Monday. Not sure exactly when that's going to happen. Okay? But sine's equal to half in those two quadrants, so it's pi 6, 5 pi 6. Although that's only if they limit you from 0 to 2 pi. They didn't really there, so maybe it should have been this. Okay? Not going to get too excited about that right now. On 18, it's another trig one. But when you do the square root of both sides, it should be plus or minus, so it should be in all 4 quadrants. So that's something to keep in mind on that one. 19 is another trig one where here we would factor out a sine. So where does sine equal 0, which is at 0? Where does sine equal negative 1, which is at 3 pi halves? Okay. Number 20, factor out e to the x. Set them equal to 0. E to the x is never equal to 0, so it's just, there's no answer there. Where does this equal 0, which would be a plus or minus square root of 2? Okay. And then this last one is just one that I wanted to show you that, you know, there are going to be some equations where we can't do anything with them algebraic. We go to menu, algebra, solve, let it solve it. Now this one had a whole bunch of solutions. If I get one that has a whole bunch of solutions like this, now what you want to do is you want to move the one over, set it equal to 0, graph it, see where it crosses the x-axis. See how many times it crosses. Normally this would be limited, like, you know, usually that's not going to be an issue that you have all these different answers. There's usually a set limit of where you're looking and so forth. Okay, so I just realized that Sam, who, if he watches this video, we'll quiz him tomorrow. Was looking at this the whole time we were talking about that. See if he said. Okay. 2.4 homework question. There were two main, well, I should say 3. 2 main ideas. One of them has got two parts to it. All right, so the first part I want to make sure we understand is that thing about big F. This is, uh-oh. Oh, darn it. Yeah, I was going to say, we just have to not do anything. But it's working, so I guess we can. All right. So what is big F? Antiderivative of F. Now, I'll probably say little f most of the time, but let's agree that if we say F, we mean little f. right? Because that's what we've been talking all the time. So when we say F, we mean little f. Capital F, we're going to say big F. Okay? So we want to make sure we make that straight. So if I say F prime, we mean, so we don't have to say little f prime and little f prime. Okay? If we're using big F, we should say it specifically. So if we're going down, we're doing the derivative. Right? So the derivative of big F is little f. The derivative of f is f prime. The derivative of f prime is f double. But also, wouldn't this row, wouldn't those two be the same? Right? Big F prime is the same as little f. Big F double prime is the same as f prime. And big F, I guess, triple prime, not that we use that one that much, but that's important to understand. All right? And especially if we have the chart up here. All right? That this would be, the top row here would be the equivalent of big F, could be the equivalent of big F, right? So we could label this, well, I'm not going to, I guess, but we could label this big F, F, little f, and little f prime, right? So big F, F, F prime. And so if we were to look at problems 3 through 12, would it be worthwhile to go through those?
Yes.
Yes? Okay. I think so. I mean, you would all be amazing if you all got that right. However, if you went through 3 through 12, if you spent some time going through 3 through 12, I hope you noticed that those questions could have been in chapter 1. There isn't a single thing on those questions that we couldn't have done in chapter 1. Matter of fact, now that I just say that, this would be a good time to look at these old quizzes. Does anybody care?
Yes.
Yes, because you don't want to see it.
I don't even know.
You do want to look. Now these are the old quizzes, right? Not last week.
Yeah.
Right. Okay. That was my intent. My intent was before I even got to this, but actually,
Was it the first verse or was it the second?
this is the second. What we did pretty good. Okay. Because if you yeah, we did pretty good. A few people passed. That's nice. All right. But this quiz was about the chart. Okay, so this fits in quite well with what we're doing here. Carrie.
Oh, it's like, I got the answer right, so they can one. That's fine, this one.
John. Give that to John, please. Natalie. Richard. All right, now. Okay, couple of comments here. On number one, the key thing that most people miss is the G stood for gas mileage, miles per gallon. Now I don't know why we missed it because that's the very first sentence, but it's miles per gallon. And S, the input, is the speed. So the statement, the 55 is the speed. Now I didn't designate what the speed unit's for. I think some people asked me, and I said whatever you want. Or some people just said per unit of speed, which is fine. Now a lot of you just assumed it was miles per hour and just went with that. That's fine too. But at 55 miles per hour, the gas mileage, G, is decreasing. Because G would be like the top row here. And when G prime is negative, then G is decreasing. So the gas mileage, the miles per gallon, are going down 0.23 miles per gallon for each mile per hour of speed at 55 miles per hour. Now, some people said at 55 miles per hour, you're getting 0.23 less miles per gallon than you were at 54 miles per hour. That's another good way to say it. But some people were getting all mixed up with units in there. You thought 0.23 was gallons or miles. It wasn't either of those. It was miles per gallon. Okay. Anything else on the front page? Number 4, and I don't want to get into real big discussions about any of them. I just mostly want you to see them. But number 4 down there at the bottom, this is where we talk about the chart. This is the thing we're getting back into now again here in chapter 2. Where is the function increasing, decreasing, concave up, concave down, that kind of stuff. Okay, go to the second page. Second page, we did pretty good. There wasn't too much there, really. On 7, we might talk about the true false real quick. I think I had kind of said that the trues you didn't really have to have an explanation for. I mean, some of you took it early and you may have had an explanation. I didn't count off your explanation, I don't think, if you had it true. Okay? Because basically if it's true, you're just restating the statement. I mean, so there's not much there to say. But if it's false, why is it false? And one that people miss, like on A, is false. Because people were trying to say, well, it could be true. Well, if it could be true, then it's false. You get what I'm saying? I mean, the if f prime of A equals 0, then f has a local max or local min. That's not true. Could have a local max or local min. That's not what it says. It said it has a local max or a local min. What's it missing? Flat spot. If f prime is 0, then it's a local max, a local min, or a flat spot. Okay? That's a true statement. The way they wrote it, it's a false statement. Okay? And then C is also false. It's concave up not when f prime is positive, but when f prime is increasing. Okay, go to the next page. On 6 there, again, we did a pretty good job. I thought we got pretty good at looking at those graphs and looking at the chart and knowing about increasing, decreasing, so that was good. And then 9 had some true, false. 8 was false. Again, if f double prime is 0, then f has inflection point? No. It's a possible inflection point. What has to happen with f double prime? Or what has to happen with f to be an inflection point? What has to happen for there to be an inflection point? F has to change concavity, or f double prime has to change positive to negative or vice versa. Okay? Which usually happens when f double prime is 0. We're going to talk about that today. It usually happens when f double prime is 0. But just because it's 0 doesn't mean it changes sign. And then D is false. It's not when f double prime is positive, it's when f double prime is negative. And then on number 10, and this was my screw up, which was kind of a benefit for you guys. Yeah, there were supposed to be 46 points here, but that's because the last one was supposed to be worth 2 points. And like a dummy, I told somebody, I think in the other class, they'd asked me something about zooming on their calculator, and I think I told them they wouldn't have to. And then sure enough, I had one on there where they said to. So instead of having, so I made it out of 44, and I gave you a bonus point if you got it. So that's where the bonus point came from. So, I mean, this was supposed to be pretty easy. I mean, what height? 50 feet. I think some of you might miss it because you thought it was too easy. It must be harder than that. What's initial velocity? 24. That's what that means. Was it going up? It's up. Why? Because the 24 is positive. Since the velocity is positive, ball is going up. Some people say, well, I graphed it and the graph was going up. Or, you know, I mean, you did have a calculator, so I understood that. So, so there was a few that might have lost a point because you didn't kind of make that connection to the velocity or connection to f prime, that kind of thing. Okay? And then this was negative 40. And by zooming just means get 2 points really close to 2. So do the derivative, and I wanted to show the setup, so have the slope calculation there, zoom in, do the calculation, you get negative 40. So if you got that, had your work and everything, that was a +1. That's what that was about. Okay? All right. Let's pass those back in. And if you have, if there's some you want to go over, And if if there were some that you didn't do well on, you should. Because certainly, as you will see here, this stuff with the chart is going to continue to be very important. And we're going to see how that plays out here today. All right. Now, back to this homework. So on 3 through 12, I would submit to you that on 3 through 12 is no different than one of the problems we just had on that quiz. They give you a graph of what? Big F? No. It's little f, isn't it?
That's why I'm having difficulties.
Okay. They give you, hang on here a second. Let me, they give you a graph of little f, but then they ask you a bunch of questions about big F, right? So when they give you this graph right here and say that's little f, isn't that also big F prime? Right? Isn't that the same thing? So when they ask in number 3, what is the slope of big F at 4? See, and this is where, like on this quiz we took last week with the limits and stuff, I'm a little nervous about our lack of ability on notation. I mean, I think that's where people were getting fouled up with the limits some and a little bit, and I still continue to see this. When you read that number 3, my hope is that the first thing you would think of would be to write that right there. When it says, what is the slope of big F at 4, my hope is you would write that down on your paper. Because I think that proper notation helps tell you what the problem was. And if you don't know what the notation is, then reading the directions, and I think what happened on this last quiz a little bit is knowing what they're asking for. You don't know what they're asking for because you don't know what the notation means. Big F prime of 4 would just be the y value on that graph, right? That's it. Where is big F increasing? Look at your chart and let's make the top row big F. So when's big F increasing? When little f is positive. When's that? The whole time, from 0 to 10. Right? Where does big F have points of inflection? Isn't it here and here? Right? Yeah, it's when big F prime has its local max and min. When it changes increasing, decreasing is when big F would change concavity. We knew that from before, right? When the derivative had local max and mins was when the original had points of inflection. So this is nothing new other than the notation of big F. Once we got that understood, then this is the same stuff from chapter 7. Okay. Where is big F concave down? Well, that would be when this graph is decreasing. So from this point, 1.4 something, to this point, 8 something. Estimate big F double prime of 5. Well, big F double prime would be F prime, little f prime. Well, this is little f, so little f prime of 5, wouldn't it just be this slope right here? Rise and run, what is it, 1.5, somewhere in there, roughly? Negative, yes, thank you. Negative 1.5, negative 3 over 2, something like that. Why does F double prime have its minimum value at that inflection point right there? Well, what's that? Because it's the inflection point. Now, it'd be good to go a little more than that because of if it's local. I mean, that's a local minimum. We talked about that. But why does F double prime or little f prime have its minimum value? Well, how can something be its littlest value? Well, it's either the least positive or most negative, right? That's how it would be its littlest value. Well, this at this is where it's the most negative, the slope, right? F prime. We're talking about big F double prime, which would be the same as F prime, which would be the slopes of this graph. And the slopes of this graph are at their most negative at that inflection point. The steepest going down. For now, that would be a good explanation for that. Okay, this is important. Equation of the tangent line of L. They told you in the directions. Some people that came and asked me about this didn't even know what L was. They didn't read the directions. In the directions, they tell you line L is tangent to the big F graph at x equals 0. Now, again, you guys have done a good job of this point slope form, but what we haven't done a good job of is understanding the notation again. Here's what I want to start seeing you do. You know, the first thing I told you to start doing is when you read equation of tangent line is to write this, right? And so you did a good job of that. Now I'm telling you, when you read find the equation of tangent line, I want you to do this. You need two things. What are they? Point and slope. You need point and slope. Now I want to quit saying point and slope. I want you to start saying this. If I want the tangent line to big F at 0, I want you to say, okay, I need two things. I need point and I need slope. Right? Isn't that what I need? I need big F at 0, which is the point, and I need big F prime at 0, which is the slope. Those are the two things I need. Well, they told me big F of 0 was 10, right? And big F prime of 0 is nothing more than little f of 0, right? Little f of 0 I get right off the graph. That was 7. So once I have those two things, I got y equals 7, x minus 0, plus 10. But the key is that when you read find the equation of the tangent line to big F at 0, you say, okay, I need a point, big F of 0, and I need a slope, big F prime of 0. I need those two things. Once I have those two things, I got my equation. Okay? Again, the notation, once you write down the notation, then you got it. Because it tells you where to plug it in, it tells you what graph to look at, okay? It's all there if you got the notation. Yes, you can absolutely leave it like that, that's fine. Or you can just have 7, you can simplify it too, that's fine. All right, now the last three are good, because again, just like in chapter 1, they make us think a little bit. Does L lie above the curve at 1? So we got to start thinking, tangent lines above the curve, what would that look like? Well, it wouldn't look like that. Or like that, aren't those tangent lines that are above the curve? What would it take for a line to be below the curve? Have to look like that, wouldn't it? So it's the concavity that determines that. So this question is really in disguise asking, is big F concave down? Right? It says, does it lie above the curve? Is saying, is big F concave down? You look at your chart, big F's concave down when little f is decreasing. Hopefully we don't have to look at the chart anymore, right? Big F is concave down when little f is decreasing, which would be from 1.4 to 8. Oh, wait, but they asked us at 1, right? They said at 1.
So it's a yes or no.
So it's a no, right? Isn't it no? Because at 1, we're back here. So big F is increasing. So therefore, or excuse me, little f is increasing. So big F is concave up. So if it's concave up, the tangent line's got to be below the curve. So this is no. Okay? Is it possible that big F of 5 is equal to 5? This sounds like what? Speak. Yeah. I wish Dr. Dostal had been in here for this class. Second block let me down. He was in here and he was kind of doing the walkthrough thing. And also, and then when he left, and then I told him they was marking me down because they thought of speed up law eventually. And then I realized I still have my goals up for computer math and not, I don't have my AP Calc goals. I think I got done. See, and you're just like the other class. They said I was getting fired too, and they kind of had a smile on their face when they said it, just kind of like you did. All right. So, no, nothing important. Not like you guys, where you did not that's amazing. Yeah, right. Yeah, like when you're tardy, yeah, those lunch detentions you guys been serving really, and
I'm actually never.
oh, Has anybody in here ever been targeted?
Twice.
Right. It was Sam once. This
Yeah,
one?
I just need it for more time.
One more time. Does anything really happen?
I don't know. Do you give out little shit?
Nope. That's the office.
Yeah, but if you didn't put it in the computer, then you would get it.
No, it's literally happened.
No, the teachers have to put it in there.
No, you get those slips.
My mom.
I think you're right. The teacher's putting it in.
Yeah,
So
the
what
teachers.
ended up
Every
being one or
time
two.
that I've been late here, my mom gets a call.
Yeah, my mom gets the
She's
same
like,
call.
why are you at school right now? I
For-
was like, sorry, mom. I was
For this
late."
class or like all classes?
For all of us.
Oh. Well, really?
Yeah.
Like if you're like, then you said it and you don't change it. and it's-
Yeah, I was gonna say, if I mark you absent and I forget to change it to tardy, you'll get it. But I don't think just for tardy. But a lot of times the teachers don't change it till later. Well, you know what happens in this class, especially because I think they start making those calls like in the afternoon or something. I think for the morning when they start or something. Anyway, could big F of 5 equal 5? Could be, yeah. If you want it too bad enough, it could. Could big F of 5 equal 5?
No. No.
Here's the key. Remember, we gotta go back to that. Big F of 0 is 10. So if we were, remember when we had big F, not big F, but we had F prime graphs and we drew F? Well, what we have here is a big F prime graph, and so we could draw F, and at 0 it's 10. So what could 5 be? Well, if we go over 5, what would we have to do? We'd have to go down. Could we go down on this one?
No.
Because this graph is a slopes, right? And this graph's always positive. Since this graph's always positive, big F graph has to go up. Can't go down. Speed limit law. So the slopes are always positive, so there's no way this goes down. Okay, so the next one's a little trickier. Could F of 5 equal 15? No.
No. No.
Because if it goes over 5, to get to 15, it would have to go up 5.
There's no slope.
Goes up like 7 first.
Look at the graph.
Goes up 7.
Yeah, what are these y values? These y values are the slopes. It's 7, 8, 6, 5. I mean, look at the graph.
3, 2, 1.
So close. Right on it, right on top of it. There's calculus level and you have to make it fun. I agree. And that was fun. So could it? Yes or no?
No.
Because the slope would have to be
Below the 5.
1. Would it have to be 1 to go over 5 and up 5? Slope would have to be around 1. Have to average kind of 1. The first half of this graph, the y values are way above 1. Way above. So it's got to go up much steeper than that. So not only could it not go down, it's got to go up much faster than that. So both of those are good. All right.
I don't think that was the right reason.
If your reason was because of 3, if your reason was because of 3, 2, 1 blast off, then yes, you probably did not have the right
No,
reason.
it blew up.
Because it blew up. So that's.
How'd you spell that?
All right. So hopefully that part of section 2.4 is easy. I mean, easy in the sense that it's the same as chapter 1. It's just this big F, this idea of antiderivative. And so it's those same connections, all the same connections to chart. All right. Here's the more important part of all this stuff. Here's the part we have to be able to do. Okay, everybody stand up here and take a 30-second break. 30 seconds.
Your arm.
I was just laying on my bed.
I really could have got
All right, here we go. Here we go.
No. There's 7 short stories. Each has its own little twist. And then they all get together.
All right, let's take a look at number 19, please. All right. Now, we're going to do number 19 and we're going to do number 23. There are 2 problems that are similar looking, but and we start them kind of the same way. What is going on? Now I want to say similar. I want to say funny looking. Okay, they're similar. What? Similar.
That's funny.
Look at that. Yeah, now this is, you're screwing this, you're making this screw up. All right, so 19 and 23, very similar looking problems. Is it minus a 19? 3x squared? And that's x cubed. Okay, x cubed minus 3x squared plus 5. So they're very similar looking problems, but, and they're approached in the beginning kind of the same, but then they take kind of different twists at the end in what we're looking for. And so it's very important you understand what the problem is asking for and why you do. I mean, I don't want you to memorize, oh, if it says do this, then do this, do this, do this. I mean, you should do it because you know what you're looking for and you know why doing it this way gives you that information. Okay? So I call a problem like this chart stuff. All right? If you look at what they asked for in 19, and they say in the directions, they say give your answers exactly rather than decimal. In other words, no calculator is what they're saying. In a problem like that. Don't, this is a no calculator problem. So what we have is a cubic equation, f, and we want to know, what do they want? They want to know where is it going up, where is it increasing, where is it decreasing, where does it have a local max, where does it have a local mean. Now if you look at the chart, those are the things that are in the chart. Where does it have a local max? Where does it have a local min? Where is it increasing? Where is it decreasing? Okay? That's those 3 parts there, which means we want to focus on those 3 parts there. Where does f prime, 0, positive, negative is where we're going to be interested in. See, now we're used to doing this from a graphical perspective. But now in chapter 2, we're going to be working with equations. So if we want to know where f is doing this stuff, we've got to figure out where f prime is doing this stuff. So the first thing we need is to get f prime. So I can go back to here. So f prime is what? Okay, that's f prime. Now, again, back to the chart. I guess you get it. Back to the chart. We need to know when that is 0, positive, and negative. Now, those 3, what's it going to be easiest to figure out? Where it's 0. So we almost always, and we did this problem, a problem like this last Wednesday, we almost always start out by setting the derivative equal to 0. Matter of fact, many times this year I'll say to you, if you don't know what to do the derivative, set it equal to 0, that's usually a good start. And this is where 19 and 23 start out the same, and then they kind of deviate from there because of what we're trying to figure out. All right, so what do we do to solve it? Now you can see why we did the algebra review worksheet. We're going to be getting to here, we're going to have to solve it. Now, when we get to section 2.5, this will be an e to the x equation or a log equation. When we get to section 2.6, this will be a trig equation that will be solved. Okay? All right, so what do we do right now? Factor out an x. We could have factored out a 3, but it doesn't matter. So x equals 0 or 2. Now, since that's where the derivative is 0, I should just maybe label those. Those are called stationary points, right? Now, let's stop here for just a second and remind ourselves what we would have been doing in chapter 1 when we were talking about local max, local min, and stuff. In chapter 1, we were dealing with graphs, not equations. So if I would just stop for a second and look at this graph here, this f prime, that's a parabola. I hope when you look at that, you would see a parabola. And not that, but it's a parabola that opens up. And what did we just find by setting it equal to 0? Where it crosses the x-axis, right? So because this is such a simple function, most of the time or a lot of the time, it won't be that simple. But since it's such a simple one, and we know what its graph looks like, off to the side here, I wouldn't write this. I mean, you can if you want, but normally we would not do what I'm doing right now. Because normally we would not know what this graph looks like. Okay? But now we do. It's a parabola, and it crosses there and there. Isn't it going to be this here?
Yeah.
That's my f prime graph. This is what we were used to doing in chapter 1. And the fact that it was positive and then went negative and then went positive was kind of important to us, right? Matter of fact, with that information, we could now answer the question. The question says, where is f increasing? Now, f, we mean the original. Where's the original increasing? Well, if this is f prime, it was increasing when? From negative infinity to 0 and from 2 to infinity. Where is f decreasing? When f prime is negative. From 0 to 2. Where does f have a local max? At 0. When f prime changes from positive to negative, f goes from increasing to decreasing, right? And where does a local min? So if we have this information, right? Now go back to the chart. If we know where f prime is 0, positive, and negative, we know all of this about f, right? And in chapter 1, the graph told us that. But now let's imagine, and now pretend this wasn't here. Okay? So now let's imagine that we didn't have the graph, and all we had was this. How can we get that same information? Well, since I know that f prime is 0 here and here, I'm going to do what we're going to call an f prime number line. So when you hear me say do a number line, okay, do an f prime number line, this is what I'm talking about. Okay? So I do an f prime number line. Now again, one of the things is going to, over the next couple of days, I've already had some people from Second Block come in and lunch and ask about this. Why did you do a number line? Why am I doing a number line? Because I want this information. The question's asking me where f is increasing, where it's decreasing, where it's local max, local min. I need to know when f prime is positive or negative or 0. A number line will give me that information, just like a graph gave me that information. So here's what I do. On my number line, I put hash marks for my 0 and my 2. Okay? Now, some books, some teachers will put zeros above that. Okay, that's where f prime, see, I always should label this number line with f prime. So that's where f prime is 0, at 0 and at 2. How would I tell if it's positive over here?
Put some value over there.
Let's just pick a number over there and plug it into f prime. Let's put in -1. And in here, let's put in 1, and in here, let's put in 3. Now, don't put hash marks for those. I always see people draw number lines, and they put hash marks every time, and then it's just a jumbled mess. Okay? I've got 3 intervals here that I want to look at. So I just put some little numbers there that I'll plug in. So I take a -1, I got to plug it into f prime. Now, I can plug it either place. I can plug it into that version in the box or this version. Usually, the factored one's easier. Because all I care about if it's positive or negative. I don't really care what the value is. So I put a negative 1. I'm going to put it here. Put a negative 1 there. What do you get if you put negative 1 here? Negative 3 minus 6 is negative 9. I don't even care if it's negative 9. It's negative. Negative times negative is positive. Put a 1 in. I'd have 1 times 3 minus 6, which is negative. Negative times positive, negative. Put a 3 in. 9 minus 6 is 3. 3 times 3, 9, positive. Doesn't that number line give us the same information the graph gave us? Exactly the same information. So, where is f increasing? From negative infinity to 0, from 2 to infinity. Where's it decreasing? From 0 to 2. Where's their local max? F prime changes from pi. Now I'm going to tell you how I specifically want you to write this here in a second. But local max is there, local min is there. Same information we were getting in chapter 1 with our graphs, we now get from this number line. And it even works on ones where we don't know what the graph looks like. So we can do this number line. Okay? So but the reason we did the number line is because we wanted to know what the graph was doing this way. We wanted to know it's up and down and peaks and valleys. So this number line tells us that. We didn't care what it's like. Notice we never plugged anything into f, the original. Now, on the next problem, we're going to. And that's where it's going to get different. You got to understand the difference of why we do one and not the other. So here we plug into f prime because we care about when f prime is positive or negative, it's from the chart. Now, here's how you have to write your local max answer. I just want you to be very clear about this. We would say local max at x equals 0, and local max will almost always ask you to justify your answer. So we would say, since f prime changes positive to negative, f changes increasing to decreasing. We've got to say that. We've got to say that. Both the f prime and the f part. In that packet I gave you at the beginning of the year from the AP, about the AP test and stuff, they talk about that very thing right there. You've got to make that connection between f prime and f. And I will, on the next quiz, there will be questions like that, and I will be looking specifically for that. You've got to have that in there. Okay? Now, and when it's increasing, you don't have to say because f prime is positive. Usually that's not a big deal. On local max, local min, I want you to justify that. Okay, very quickly. It didn't ask for it, but I want to do this. What else is in the chart? Besides local max, local min, and increasing, decreasing, the other thing that's in the chart about f is inflection point and concavity. So let's say the question had asked this as well. This is what I mean by chart stuff. The question asked about concavity, inflection point, local max, local min, that's chart stuff. So what if they wanted the inflection point? Well, where on the chart, where do you look for an inflection point? When what happens? When f double prime is 0. Put the chart back up here. These three things, 0, plus, minus, tell me about this stuff. For this stuff up here, inflection point is when f double prime is those things. Wouldn't a number line work good again? Except to be an f double prime number line this time. So if I've got an inflection point question, I'm going to want f double prime. Well, that's the derivative of f prime. What is that? And I'm going to want to set that equal to 0. Now let me just back up a second. We already know from chapter 1 that if this is my f prime graph, where's the inflection point of f? Isn't it right there? Which I believe would be halfway in between here, which would be at 1. We'd expect it to be at 1 from our chapter 1 stuff we learned. But pretend we didn't know this. So we do the second derivative, set equals 0. What do we get?
1.
X equals 1. Now remember, that's a pip. That's a possible inflection point. Those are stationary points. This is a possible inflection point. We don't know until we do a number line. Okay? So, we draw a number line. Here's why it's important to label these. This one's an f double prime number line. We put our 1 on there, but we care about what's on each side. So we pick a number over here, say 0, pick a number over here, say 2, and we plug it where? That's why we label that f double prime. We're going to plug it into there. We want to know those values. So we put a 0 in, what do we get? Negative. Put in a 2. What's that tell you if f double prime is negative? F is concave down. F double prime positive means F is concave up. We had to change the concavity there. You need to do this like you did for local max for inflection point as well. Anytime there's that change, you got to write it. So you'd say inflection point at x equals 1, since f double prime changes. Now here we wouldn't have to say negative or positive because it doesn't matter which direction it changes. All we need is for it to change. So if we say since f double prime changes sign, this is good enough. Since f double prime changes sign, positive, negative, either way, f changes concavity. So when you use that number line, on the AP test they tell graders, because I graded test one summer, they tell us to ignore the number line. If they have a number line, ignore it. It's this that they look for your reason. The number line is just for your help. The number line is for you to gather your information about the problem. But then you pull that information off of there to answer the question. And if it says justify, you've got to write down and communicate what information is there. So the number line by itself is not a justification. It's for you to gather your information. All right. So doing number lines tells us, f prime and f double prime tells us about the shape and the concavity and that stuff, tells us about local max, local min, those things. Chart stuff. Now, number 20 is not part of your homework, but I would strongly suggest you try to do number 20 tonight. See if you can repeat what we just talked about with number 19. Okay? Final thing we're going to do is number 23. And we're going to see how it's different from this one. There's some similarities, but then there's some differences. On this one, it's about global max min. Now it's a similar problem. This time it's x squared minus 3x plus 5. It's not 3x squared, it's just 3x. It's cubed again, thank you. It's cubed. Okay, so again, we have a cubed. But this time we want global max min. Now what's that mean? Actual highest and actual lowest value. Now, in the last problem, did we ever plug anything into f? Did we ever care about the y value of the f graph? No. We just cared about the shape and where it had its local maxes and mins and inflection points and stuff. So our answers were always at x equals this or x equals that, or in intervals. Now this is different. Here we want the actual value. If I've got a graph here that goes like this, oh, and by the way, on this one they tell us it's from 0 to 2. Usually we get endpoints on these as well. What's my highest point on this one? At this local max. Where's the lowest point? At the end point. Now if you think about it, if there's going to be a highest point in between the endpoints somewhere, where's it got to be? If there's going to be a highest or lowest point in between the endpoints, doesn't it have to be at a local max?
Yeah.
Or local min? Doesn't it have to be at a place where the slope is 0? Now it could be at a sharp point, derivative undefined. We don't want to mess with that right now. So we'll just say it's nice and smooth curves that we're doing. Does it have to be at a stationary point? The highest or lowest place? Or at an endpoint? There's nowhere else it could be. Now, think about this. If I wanted to know the biggest value of this and the littlest value of this from 0 to 2, one option would be like plug in 1,000,000 numbers between 0 and 2. Right? But who wants to do that, right? I don't want to sit here and plug a bunch of numbers in. And who's to say I would find the right one? Right? We don't know. We can't just start plugging numbers. But that's what we want to do. We do want to plug numbers into here and see what the highest is and what the lowest is. Because that's what they want. It says find, they didn't use the word global, but it said find the max and min value. That means the biggest and littlest output. That's different than what they were asking in the last question. So we're not going to do a number line. Number line just told us what the graph was doing. We need to actually plug values into this. But the question is what values? Well, that's what I was just saying. The only places the max and mins can be is at the stationary points or the endpoints. That's it. And stationary point, remember, is when f prime is
0.
0. Those are the only places we have to look. Those are our only candidates to be maxes and mins. The endpoints and the stationary points. And we need to then plug those in where?
Left.
No, into the original. See? This is where we're going to plug them into the original, because we want to know what the highest value of f is and what the lowest value of f is. So we're going to actually be plugging these back into the original. So we already have our stationary point, so I'm going to even start that. I'm going to call it LOC, list of candidates. I'm just going to make a list of my possible y values that could be maxes and mins. One could be at my left endpoint, so I'm going to need f of 0. And one could be at the right endpoint, so I'm going to need f of 2. Do you understand why I'm plugging them back into the original? Because I want the biggest and smallest output of the f graph. So it could happen at the endpoints, like this picture shows. Or it might happen in between when the derivative is 0. So don't I need to do the derivative and set it equal to 0? So this part is like the other one. 3x squared minus 3 and set it equal to 0. So divide by 3 or factor out of 3, right? You could leave the 3 if you don't feel comfortable dividing by it. You could divide by it, but you got to be careful. If that was an x, you wouldn't want to divide by it. Okay, does 3 ever equal 0? No, so we basically ignore it. X could be a 1 or a negative 1. But it can't be negative 1 because that's not in that interval, so we would throw it out. Okay? So what that means is 1 is one of our candidates. We have to plug that into the original function too. Our minimum or max value could be at 1. It's got to be at a stationary point or an endpoint. So what we've done is instead of having to plug a million things into the f function, we've narrowed it down. The only places the max and min could be are at 0, at 2, and at 1. Now I know these two problems are confusing. A little bit. Can be confusing of why we're doing 1 versus the other. So we really got to, I didn't want to work on one for a while and then work on the other for a while. It's still confusing. I mean, so let's just throw them both out there and then let's just work on the differences between them. So what I'm going to do is now, so I don't need to do a number line. That doesn't help me any. Number line just tells me if it goes, I mean, I could have a graph that has, right? A number line would tell me that I have positive, negative, positive, negative, positive. It tells me I have a bunch of local maxes. Well, what do I really only care about? I only care about the one that has the highest output. So I would take this one, this one, this one, this one. I'd plug them all into the original. They'd all be candidates. I'd plug them into the original. I just care about the one that has the biggest output. So let's put a 0 into this. What do we get? 5. Put a 2 in. 7. Put a 1 in. 3. Now the question said, find the max and min value of f. So what's the max value? 7. So when I answer this, I would do this. I would put a box around the 7 and say global max right there. And the min, global min is 3. So I know if I was to look at this graph of f, between 0 and 2, its highest y value would be 7, and its lowest would be 3. And I knew that because I narrowed down where to look. I didn't want to plug million numbers into f and find its y values. I knew that by being smart about it, the only places the max and mins could be, the highest and lowest points could be, is be where the derivative is 0 or at an endpoint. So I did the derivative, set it equal to 0, found that as one of my candidates, took my endpoints as my other candidates, plugged all of those into the original. The biggest one's my max, the littlest one's my min. So 25 is one of your assigned problems, so it's like 23. So here's what I would suggest. Your homework is really the 2.4 homework questions. Now we already talked about a lot of them. Now 3 through 12, we're kind of chart, here's a graph, kind of chapter 1 kind of stuff. 13 through 18 is another section that does that same thing. So if you want some more practice, I would suggest looking at 13 through 18 as well. They give you a graph, they ask you some of those same questions, so it wouldn't hurt to look through those. I would suggest doing number 20. Didn't assign it, but 20, 21, 22, those are like 19. So those would be good practice, because these last two things we've just done here, number 19 and number 23, see those a ton over the next 3 days. We're going to see it with exponentials, with logs, with trig. It's going to be a big part of the next quiz. Big part. Okay? Problems like number 19 and problem number 23 are going to be a big part of it. We're going to learn some new derivative rules for e to the x and ln x and trig and stuff, and so that's also going to be a part of it. And then we'll apply them in problems like this. Okay? So you'll hear me a lot over the next 2 or 3 days. Hey, go back and do one like number 19 or one like number 23, and, or this is like number 19 and this is like number 23. Okay, so those are two pretty important problems right there. I've even got